So we already know that halogens are oxidizing agents. What we're going to look at now is we're going to look at halide ions as reducing agents. So let's just recap why halogens are oxidizing agents first. Okay, so remember, if I've got a halogen here, or a slightly larger halogen, an oxidizing agent gets reduced. Remember, reduction is gain of electrons. Reduction is gain of electrons. So fluorine is a halogen. There's a greater attraction between the electron and the halogen. However, iodine, there's a smaller electrostatic force of attraction. So F2 is a stronger oxidizing agent than I2. We did that in 10.2. So there's an explanation of why that is, and the evidence comes from displacement reactions as well, doesn't it? So we know that halogens are oxidizing agents. The reason why they need to be oxidizing agents is because we need to fill the electron shells, so we're trying to gain electrons there. Now, halides are reducing agents. Remember, halide ions have already got that electron. So we have an F minus here, it's quite small, and an I minus, which is much bigger. So an oxidizing agent gets reduced. Reduction is gain of electrons. A reducing agent gets oxidized. Oxidation is loss of electrons. So halogens are oxidizing agents. Halides are reducing agents. So they get oxidized, they lose electrons. So it's going to be really difficult to remove that electron there from that fluorine, that fluoride rather, because this electron in the outer shell of fluoride is very close to the nucleus. Also, there's not many shells between that electron you're trying to remove and the nucleus. So there's a very strong electrostatic force of attraction between the electron you're trying to remove and the nucleus. Whereas the electron you're trying to remove from an iodide ion is much further away from the nucleus. And there are a lot of shells between the electron you're trying to remove and the nucleus. So there's a lot greater shielding, so it's much easier to remove. So the trend flips. So as we go down the group here, the halogens get weaker oxidizing agents. They're not as good. However, when we go down the group here from fluorine to iodine, or I should say now fluoride to iodide, then they get better reducing agents. And that's due to the ionic radius. Because the ionic radius increases, then the ability to reduce something increases as well. Okay? So what I want you to do is I want you to write down a full explanation of why that is. So I'm going to start the sentence off for you, and then you're going to finish it, and I'm going to give you some keywords to use. So there's your sentence starter. F minus is a weaker reducing agent than I minus because, so let's have a look at this. So what we've got here is we've got a much smaller atom, a much smaller ion there with a lower ionic radius. So I'm going to put that as a keyword, ionic radius. Electrostatic attraction, distance, the distance between the electron you're trying to remove and the nucleus is a factor. Shielding, not much shielding there, but quite a lot of shielding there. Okay, so have a go at answering this question here using those keywords. So we're going to look at the evidence for that then. So the evidence of halogens and their oxidizing ability comes from the displacement reactions. We can look at the evidence of the halides as reducing agents from a different set of reactions. And what we do is we look at the reactions of sodium halides with concentrated sulfuric acid as evidence of how good they are at reducing agents. Okay? So solid sodium halides, so sodium halides are things like NaF or NaI, they react with concentrated sulfuric acid. And because they react with concentrated sulfuric acid, what's happening to the halides is the halides are all getting oxidized. So they're acting as reducing agents. They actually reduce the sulfuric acid. And we can look at to what extent they do that determines the reducing ability of the halides. So we can actually look at the products of these reactions to reflect the reducing powers of the halide ions. Okay, that's what we're going to do. Okay, what we're going to do is we're going to work down the group. So we're going to start with chloride ions. So we're going to start with chloride and then we're going to work down to iodide. So we're going to look at how good that is at reducing sulfuric acid. So we're going to do this little experiment here, and our reaction is if we pick a halide ion. So here we've got a sodium halide ion, and we get some solid sodium halide, and react that with concentrated sulfuric acid. Now, you need to be careful here because the state symbol for concentrated sulfuric acid would be liquid. Can't be AQ because that would suggest that it's been diluted a little bit with water. So concentrate, there's no water in it. So I've got solid sodium halide and concentrated sulfuric acid. And we're going to look at the products of these. Okay, So this is called sodium hydrogen sulfate. That's a solid that's produced. So sodium hydrogen sulfate. And this is not sulfuric acid, it's hydrogen chloride. Because hydrochloric acid would be dissolved in water, so it'd have a state symbol AQ. But this isn't. This is gas. Okay, it would only be AQ if dissolved. So this is HCl gas. Now, HCl gas, what you'd see there is steamy fumes. Okay, it looks a little bit like white smoke. Okay, but the correct description is white steamy fumes. That's what you would see. So we'll definitely have a go at this experiment, but if you imagine you've got a test tube here, and in there you've got a solid, sodium chloride, in other words just table salt, and then you pour in concentrated sulfuric acid. You get sodium hydrogen sulfate, which is just a white solid as well, so you can't really see that. You start off with a white solid and end up with a white solid, but what you find is you see these steamy fumes that are produced here, and these steamy fumes are the HCl gas, the hydrogen chloride gas, which are white steamy fumes. And that's how you know a reaction's happened. Okay, now let's have a look at the oxidation states of all these elements here, before and after. And this is why we do topic 7 before topic 10. So if you're doing this lesson now and you have not thoroughly done topic 7, you really need to go back and do topic 7 first. And you would have found that when you were doing 10.2 as well, if you hadn't studied topic 7 in a lot of detail, particularly 7.3. So it's quite a long lesson, 7.3, so you really need to go back and do that first before you go into this. It's really important, you know that. Let's work out the oxidation state of all these elements. So if you know topic 7, you'd know these. That's +1, -1, +1 on the hydrogen, sulfur's +6, and oxygen is -2. Sodium is +1, hydrogen's +1, sulfur works out to be +6 again here, oxygen is -2, hydrogen is +1, chlorine is -1. So you can see there's no change in oxidation states before and after. Sodium is +1 before and after, hydrogen stays +1, chlorine stays -1, sulfur stays +6. Now if there's no change in oxidation state, then it's not a redox reaction. So this is not a redox reaction because no oxidation state has changed. Okay, so this is just an acid-base reaction. That's all it is. It's an acid-base reaction only. So here's our acid, here's our base. Okay, so it's an acid-base reaction only. So in this particular case, the chloride here is not acting as a reducing agent. Okay, so that doesn't happen. So I didn't do fluoride, but if I did fluoride, it would act in the same way. In fact, it's even weaker. Yeah, so it would just do an acid-base reaction. It wouldn't act as a redox reaction. Now let's move down the group. Let's move down the group and then look at the bromide ion. Now the bromide ion is much bigger than the chloride ion. Okay. So the first thing that happens is that it does a similar reaction to this one here. Okay, so I can use this reaction here to work out what this one does. But actually, there's a couple of reactions that bromide does. this time I'm going to use sodium bromide, solid, and react that with concentrated sulfuric acid. So again, I'll just put some sodium bromide solid in there and then pour in some concentrated sulfuric acid. We're going to make solid sodium hydrogen sulfate, which is just a white solid, just like this, so I can't really see a visible difference here. And this time I'm going to make hydrogen bromide. Okay, so hydrogen bromide. Again, they're just white steamy fumes. So there's no need to draw this again because it's the same reaction, apart from I'm starting off and finishing off with Br minus here. And if we can work out the oxidation states before and after, and we find that they are exactly the same again. Therefore, this one is not a redox reaction, it's just an acid-base reaction again. Okay, however, bromide ions actually do another reaction, so we need to look at that one as well. So bromide ions are strong enough reducing agents to reduce the sulfuric acid to sulfur dioxide. So it actually reduces the sulfuric acid to sulfur dioxide. And you need to learn these equations. You need to learn this equation, this one, and this next one as well. All of the equations in this particular lesson, you need to learn them off by heart, okay? So I'm going to write down a couple of half equations here. So, and then we're going to pull them together to make a full redox equation. This is why 7.3, or lesson 7.3, is really important that you do this before this lesson, because I'm not going to go through loads of techniques and things. I'm going to assume that you can do it if you can do 7.3. This is why I'm going quite quick. Now, in this particular reaction, what happens is, so this is just the half equation, the sulfuric acid can actually be reduced to sulfur dioxide in this reaction, which is a gas. So we see a gas produced there. And we know it's being reduced because if you work out the oxidation state of sulfur, that's +6, and sulfur there is +4. Remember, reduction is gain of electrons. It's getting more negative there, isn't it? So we know that the sulfur is being reduced. So the thing we're just doing the reducing is the Br minus. So the Br minus is acting as a reducing agent here, because it's reducing the sulfur in the sulfuric acid to sulfur dioxide. Okay, now what we can do there is we can balance this redox equation, can't we? One sulfur there and one sulfur there, so with the element which changes oxidation state is already balanced. However, we've got 4 oxygens here, but 2 there. So I need 2 more oxygens on this side. So I need to add 2 more waters. Now I've got 4 hydrogens here, but only 2 there. So I need to add 2 more hydrogens to this side. Remember, we always add H+. So I've now got the right number of hydrogens on each side, the right number of sulfurs on each side, the right number of oxygens on each side. I now need to add some electrons to this side to balance that positive charge there, because there should be no charge on each side. So I'm going to add 2 electrons there. So you can see here, reduction is gain of electrons. So I'll put the electrons on the correct side, because I'm gaining electrons here, because the Br minus is a reducing agent. It's a Br minus which is giving these electrons. That's one of the half equations. Let's look at the other half equation. Now, we know that bromine is produced. The bromine is produced from bromide. I need, that's a solid up here. I need 2 bromines on each side. So I'm going to put a 2 here. I've got a 2 minus charge on this side. Therefore I need 2 electrons there, like that. Then I can combine those 2 half equations together. So combine the oxidation half equation here and the reduction half equation together. I'm going to check that there's 2 electrons on each side. So H2SO4 plus 2H plus 2Br minus makes SO2 gas plus 2H2O liquid and Br2 liquid. Okay, so that's our overall equation here. It's our overall redox equation. So there's an acid-base equation, and then we find that there's a redox equation. This is the redox equation here, and this is the 2 half equations which make the redox equation. And the reason why we know this is happening is because of 2 things. Okay, so we've got bromine produced and sulfur dioxide produced as well. Okay, and we'll see that. We'll physically see that browny orange colour of bromine liquid being produced. Now this reaction is a very exothermic reaction. Because it's a very exothermic reaction, it generates a lot of heat. And this bromine actually turns into a gas. So some of this bromine actually vaporizes the bromine. So bromine produces a liquid, but then what you see is, you see this browny orange gas that's produced, and that's the bromine turning into a gas because so much heat is produced. And what we can do here is, let's just look at the oxidation states again. So we said that the bromide has an oxidation state of -1. Bromine is an element, so it's got an oxidation state of 0. Sulfur here has got an oxidation state of +6, but sulfur here has got an oxidation state of +4. So whereas in these acid-base reactions there was no change in oxidation state, within this redox reaction, that's why I call it a redox reaction, there is a change in oxidation state. So sulfur goes from +6 to +4. So +6 to +4, we're gaining electrons here because we're getting more negative. So the sulfur is being reduced. I'm going to write Rig there. And we can see here that the bromide has been oxidized because it's getting less negative. Oxidation is loss of electrons. And that's because the bromide is a reducing agent. Now, if we compare this reaction here to what happened over here, the chloride didn't do this. Didn't do any of that. And that's because bromide is a stronger reducing agent than chloride. Yeah. So I've got the word reducing agent here, so it's stronger than chloride. So it's able to do that. It's able to reduce the sulfur in sulfuric acid. Okay, so we've done chloride, and we find that bromide is the same as chloride, apart from it does this extra reduction here. Now let's have a look at iodide. Now, iodide ions are much bigger still. So those electrons in iodide are really easy lost because they're quite far from the nucleus and they're really shielded, so it's easy to remove. So iodide ions are brilliant reducing agents. have a look at this one then. So the first thing which happens is exactly the same as chloride and bromide. You get this acid-base reaction. So I'm going to write down the acid-base reaction first of all. Again, steamy fumes of hydrogen iodide. We know this is an acid-base reaction because there's no change in oxidation states. It also does a very similar reduction reaction here. It reduces the sulfuric acid into sulfur dioxide. So it does this reaction here. Now we've also already balanced the bromide one. So the iodide one is identical, apart from you've got iodide ions in there and iodine in it, rather than bromide and bromine. But again, you would be expected to write down the half equations of these as well. Okay, we can work out the oxidation states of the main elements here. That's -1, that's 0. Sulfur here is +6, and sulfur there is +4. So again, we can see here that the iodide is acting as a reducing agent, just like it did with bromide, but not chloride. So we see iodine produced, okay? So you'll actually physically be able to see that, okay? So you see a dark colour of iodine as well, which is usually a black or grey solid. Remember, iodine is a solid at room temperature. This is very exothermic. Maybe some of the iodine is vaporised, but not a lot at all, because it has a much higher melting point, boiling point than bromine. But you will see that dark colour of iodine produced. Now we know that iodide ions are much bigger than bromide ions. So actually, there's not just two reactions that happen, there's a third. So the iodide ions are really, really good reducing agents. So we see another reaction here. What we see is, we see that the sulfuric acid produces hydrogen sulfide gas. The hydrogen sulfide gas is like a rotten egg smell, okay? So you actually need to learn these observations. So you get a rotten egg smell, all right? Now let's have a look at the oxidation states of the sulfur before and after here. So we'll start off here as +6. And if we work out the oxidation state of sulfur there, because this is +1, there's two of them, so the sulfur here is -2. So it goes all the way from +6 to -2, which is a huge difference. So we're gaining loads of electrons there. And that's because this iodide ion is huge. It gives electrons away really, really easy, because those electrons are really quite far from the nucleus, and they're really quite shielded as well. It goes from +6 to -2 sulfur, whereas here it only went from +6 to +4. Yes, there is a drop. It's getting more negative. But look how negative that's gone there. Now this half equation isn't balanced, does it? We've got one sulfur on each side, which is great, but we've got the wrong number of oxygens. We've got 4 there, so we need 4 on this side as well. So we need to add 4 waters to that side, so 4 H2O liquid. like that. And what else we've done here? We've got 8 hydrogens here and 2 there. That's 8 plus 2, that's 10 hydrogens. So I need 10 hydrogens on this side. But don't forget, I've already got 2 here. So I just need another 8. Like that. So I've got the right number of hydrogens on each side, the right number of oxygens, and the right number of sulfurs. I need to balance the charges now. I've got no charge on this side, so I need no charge on this side, but I've already got an 8 plus charge here, so I need to balance that with electrons. So I need to stick some electrons there. So I need 8 electrons to balance the charge. So here's my half equation for this bit. And let's have a look at what happens to the iodide ions. Okay, we know iodine is produced, don't we? We get that solid iodine. So I need 2 there and then 2 electrons here. Now, I need to think carefully before I combine these 2 half equations, because I've got 2 electrons there and 8 electrons there. We need to make sure that we've got the same number of electrons in the reduction half equation and the same number of electrons in the oxidation half equation. So I need 8 here and 8 there. So I need to times all of this by 4. So 2 times 4 is 8. 1 times 4 is 4. 2 times 4 is 8. So here is my oxidation half equation. And I can combine those two together to give the full redox equation. There we go. There's our full redox equation. And what we see is, we see the this rotten egg smell of hydrogen sulfide. Okay. So we can see there's a huge difference in oxidation state between this sulfur here and that sulfur there. And that's because this is a brilliant reducing agent. That's evidence there of further reduction. Okay. So 10.3 is actually split into 2 lessons. That's your first lesson of 10.3, where we're looking at the reducing ability of the halide ions.